Today we want to continue on from where we left off yesterday with the comparison tests. We want to do the comparison tests because we don't want to integrate everything. And we have set ourselves up for the comparison tests as if we planned it with this P-series and the geometric series. P-series and geometric series are very specific in their form and don't cover everything, but they're going to be very useful when we start making comparison tests. The idea with the comparison tests, first of all, is that we already know if the series in question is going to converge or diverge. We're not making a comparison to find this out, because in a comparison test, there are two series, one that we're given and one that we bring to the discussion. The one that we bring to the discussion, we know converges or we know it diverges. And so that's clearly what we clearly already know whether the given series converges or diverges. This is how the comparison test works. One of the series, AN or BN, is given to us, and we decide that if we're given AN, we pick a BN that we know is larger, that we know converges. So we look at AN and we say, I think that converges. So I'm going to pick another convergent series. It's always bigger. State that that one converges, and then conclude that the smaller one converges. Or we're looking at BN is given, and we're suspicious. We think, BN looks like it diverges. So I'm going to pick an AN that I know diverges. Point out that BN is in fact larger than AN, the known divergent series, and then conclude that BN diverges. So see, we already have to know. We can't just start picking things at random and testing them out. So there's two things that give us conclusion. If the larger series converges, then the smaller series converges. If the smaller series diverges, then the larger series diverges as well. If we choose poorly and the larger series diverges or the smaller series converges, then we get to not make a conclusion. We get nothing. Good day, son. That's the end of it. We've chosen poorly. We shouldn't even be making this argument. Let's look at an example. So when we look at this, 1 over n squared plus 1, let's also talk about how we're going to look at what's going on in this series. I look at the series and it's 1 over n squared plus 1. We're going to conclude that this one converges because it's like a p-series. It's not a p-series. It's not of the form 1 over n to the p, but it's close enough to a p-series that we're going to say this one behaves like the p-series 1 over n squared, which converges. So we're going to be suspicious and we're say, we bet this converges. So we're thinking for large values of n, this plus 1 doesn't mean very much. For small values of n, yeah, plus 1 is a big deal. But for large values of n, plus 1 doesn't mean very much. So we're looking at this and we're looking at what's important. And we're saying this looks like 1 over n squared. In our minds, we're saying, behaves like 1 over n squared. Oh, we should be a little more careful, even in our thoughts. We're thinking that this behaves like the series 1 over n squared, which converges. Remember, this is just thinking. So we're gonna conclude that this converges. We are already done with the important part of the problem. We have said this converges. But tomorrow we're going to be making oral arguments in front of Judge Judy. And we want to make sure all our ducks are in a row. So we can say the series 1 over n squared is a p-series with p equal to 2, which is greater than 1, which converges. The given series is not a p-series. So we want to note that 1 over n squared plus 1 is not quite a p-series. It's going to behave like a p-series in the long run. But it's not exactly of the form of a p-series. So we can't say it's exactly a p-series. So we're going to compare it to a p-series. We're going to say, first thing, note that the given series is smaller than a known convergent p-series. So we're going to say since 1 over n squared plus 1 is always less than 1 over n squared. If you make the denominator bigger, that makes the fraction smaller. So since the 1 over n squared plus 1 is less than 1 over n squared, and since the series 1 over n squared converges, if we need to justify this, it's a p-series with p equal to 2. And 2 is greater than 1. We can conclude that the series 1 over n squared plus 1 also converges by the comparison test. To use the comparison test in a formal setting, we have to show two things. We have to make our two claims. First, the given series is smaller than something that we know converges. The terms of the given series are always smaller than the terms of a series which we know converges. Given the terms of the given series are smaller than the terms of a known convergent series. Therefore, since the larger series converges, the smaller series converges. Here's another example where we have something that we're going to compare to a known convergent series, but that does not fit the description of that known convergent series. The series 1 over 2 to the n plus n is going to behave like 1 over 2 to the n. Not quite because of that plus n. This is not quite geometric, but the geometric is the important part. For large values of n doesn't matter compared to 2 to the n power. For large values of n is insignificant compared to 2 to the n. So we're looking at this and thinking that 1 over 2 to the n, that's the long run behavior. So we're thinking this behaves like 1 over 2 to the n. It doesn't really behave like 1 over 2 to the n, but we're looking at that 1 over 2 to the n and saying that's the important part. Taking 2 to the billion and then adding a billion to that is not really that important. Note that this is not a geometric series. We couldn't say this converges because it's a geometric series. The given series is not geometric. But we are going to compare it to a geometric series. So the important part of the problem is already done. We know that this series converges. If the question just says state whether the series converges or diverges, this series converges, we are done with this problem. But if we are going into court and we're going to be standing in front of Judge Judy, she is going to be super judgy if we come in here with bad arguments. And she's going to make fun of us on television, and we don't want that to happen. So we're going to get our ducks in a row, and we're going to get our argument ready to go. Since the terms of this series are always less than the terms of the series 1 over 2 to the n. Because I've made the denominator bigger, that makes the whole fraction smaller. And the series 1 over 2 to the n is geometric with a common ratio of 1/2, which is less than 1. Because of these two things, we can conclude the series 1 over 2 to the n plus n converges by the comparison test. Once we make this argument, Judge Judy will look over at the other person and make fun of them instead. And they would just have to stand there and be embarrassed on television. But it also means they don't have to pay us out of their own pocket. They get to pay us from their appearance fee. So maybe it's worth it. We have to make sure that our comparison goes in the correct direction. So in this case, our given series was set up as being smaller than something that we know converges and something that we can easily point out is obviously convergent. The problem is we have to be able to make this comparison. So as a variation on this theme, just going to use the simplest one as usual. In this case, we should be thinking that this series converges by comparison with the series 1 over n squared. And we would be 100% correct. This converges by comparison with the known convergent series 1 over n squared. But we don't get to make a direct comparison. The direct comparison does not work. The comparison goes in the wrong direction. Our given series is in fact greater than our known convergent series. If I make the denominator smaller, that makes the fraction bigger. This comparison doesn't help us. The smaller series converges. That does not help us. But we know that this series 1 over n squared minus 1 behaves like the series 1 over n squared, and that's why it converges. We are still thinking behaves like the series 1 over n squared, and that's which converges. For the same reason that large value of n, and for large values of n squared matters, plus or minus 1 doesn't matter. Here's $1 billion, and here's an extra dollar. No care. Here's $1 billion lotto jackpot, but it'll cost you $1 to enter. Cost me $1, meh. I'll only have $1 billion minus $1. You won't care. If you do care about $1, when you have $1 billion, especially $1 billion squared dollars, then we need to take all of your money from you and banish you from human society because you don't understand how money works. Actually, if you have $1 billion, then we need to banish you from society because you don't understand how money works. Enter the limit comparison test. So let's just do 3B. This is a variation on the comparison test. It still falls into the category of comparison test. And now we're going to take our given series and compare it to something that we know converges or diverges. The limit comparison test says, let's say we have two series. In the limit comparison test, I don't need to make a direct comparison between the terms. I don't need to have the terms of one being always larger or always smaller than the other. We're going to look at a limit that's because we're comparing and we're going to be looking at a limit. So that's a clever name. we're going to look at the limit as n goes to infinity of the ratio of the general terms. It doesn't matter which goes on top and which goes on the bottom. And here's why. If the limit as n goes to infinity of an over bn is equal to a non-zero constant, then we conclude both converge or both diverge. If the limit as n goes to infinity of an over bn is equal to a non-zero constant, then both converge or both diverge. This is one way we can quantify that thinking of behaves like. This is what we mean by behaves like. In the long run, 1 over n squared minus 1 behaves like 1 over n squared because the ratio of 1 over n squared minus 1 to 1 over n squared will be equal to a non-zero constant. So specifically, we'll be using a limit comparison, but a limit comparison is still a comparison. Using limit comparison test. To make this argument, we would say since the limit as n goes to infinity of 1 over n squared minus 1 over 1 over n squared. I wrote that badly. In the last minute, I wanted to save space vertically. I wrote my fraction horizontally and I wrote it badly. As n goes to infinity, limit as n goes to infinity of 1 over n squared minus 1 over 1 over n squared. This is just going to be n squared over n squared minus 1. What's going on is that the 1 over n squared minus 1 is going to 0, and 1 over n squared is also going to 0, and they're going to 0 kind of together. And that's what happens when we get a non-zero constant for our limit. So since the limits of the ratio as n goes to infinity of the ratio of the general terms is equal to 1, which is a non-zero constant, it's important to point that part out. And since the series 1 over n squared converges, we can conclude, since the series 1 over n squared converges, and since the limit as at infinity of the ratio is a non-zero constant, they both converge or both diverge. In this case, since the series 1 over n squared converges, they both converge. Remember, this problem was done 10 minutes ago. When we looked at 1 over n squared minus 1 and said that converges. That's like a 1 over n squared. This is not exactly a p-series, but it's close enough to a p-series. It's important to note that the limit comparison test would work in the situations that we've looked at, where we use the comparison test. So usually the question that comes up is, why do we have both of these tests? Why don't we just always have the limit comparison test? Because there are times where we don't get to make this conclusion. Because the limit as n goes to infinity will not be a non-zero constant. It won't exist, but we'll still be able to conclude something converges or diverges by comparison. Plus, picking one and just not doing the other is arguing to actively not know something, which is like the opposite of the point of going to school. The whole point of going to school is so you can know shit. To argue, well, we shouldn't know that part. We don't need to know that part. Let's not know that part. You're arguing to not know stuff. What's wrong with you? And then people are like, "Oh, come at me with that weak ass bullshit." No, it's not like they need to know this. They don't need to know anything. We already know that the series is absolutely convergent. Terms are always positive. We know it converges. We don't need to know any of this stuff. Why, whenever the subject comes up, yeah, but what do the students really need to know? I just get up and walk out. I ain't got time to do that. Any questions? Comments? Here's the important part, not using this in an argument in front of Judge Judy, because I'm not sure what her math background is, but it probably doesn't go this far. Understanding what the non-zero constant, this non-zero constant business, that's the important thing. Remember, it's not how, or it's not that the terms go to zero, it's how they go to zero. So this non-zero constant business, this is important. One of the things that we need to know is if the terms go to zero, but if that's not enough, we conclude that something series converges. It's not that the terms go to zero, it's how the terms go to zero. And by making this ratio, the ratio at infinity of, by looking at the limit at infinity of this ratio, when this comes out to be a non-zero constant, that means they're going to zero kind of together. If this limit as n goes to infinity of an over bn is equal to 0, that means there's not balance between the two. They're not going to 0 together. An is getting to 0 kind of faster. Because we're looking at 0 divided by something that's not even close to 0. On the other hand, if the limit as n goes to infinity of an over bn goes to infinity, then bn is going to 0 faster. And more importantly, they're not behaving like each other. In both cases, an does not behave like bn. This is a question not about bringing proper arguments to Judge Judy to win the case. This is about understanding what we mean when we intuitively decide that something converges because it behaves like something else. Why do we get to ignore all those other terms? It's not that the terms go to 0, it's how the terms go to 0. This is an exploration of how terms are getting to 0. Question? But suppose we have something in which it would be difficult to make a comparison. It'd be hard pressed to find something where this is always greater than or always less than. None of that matters because we're building an intuition. I have 5n to the third minus 3n plus 7 over 8n to the fourth plus 4n squared minus 6n plus 1. The important thing here is that we pick out the only important terms in the numerator and the denominator. In the numerator, all that matters is 5n to the third. In the denominator, all that matters is 8n to the fourth. For large values of n, these are the terms that matter. For small values of n, like if n is less than 1 especially, then n to the fourth is very insignificant. But when we're talking about n is equal to 10 to the sixth, this is what matters, 8n to the fourth. If you're plugging in a billion A billion to the fourth power is way more important than a billion squared. A billion squared is nothing compared to a billion to the fourth power. So we're looking at this and we're going to see n to the third over n to the fourth. Everything else is unnecessary. There's also the 5/8, but because there's not balance, n to the third over n to the fourth, we're saying this is 1 over n, 1 over n. So we immediately say that this diverges. Shorthand justification by comparison with 1 over n, the harmonic series. The short answer will be diverges. You can short it up quickly by saying by comparison with the series 1 over n. If you really want to deflect, say it diverges by comparison with the harmonic series, because as soon as you start using the proper name for a series, people are like, oh, whoa, using the harmonic series and just saying 1 over n. This person really must know what they're doing. And it doesn't matter. All these other terms don't matter. It doesn't matter if I can make this go to 0 faster by increasing this constant at the end. Oh, what if I make that 10? Doesn't matter. That's an n to the fourth. For large values of n, it's n to the fourth. What if I make this an absurdly large value of 10? It doesn't matter. Because eventually n is going to equal 10 to the sixth. And here's just one of them to the first power. Here's 8 of those to the fourth power. This is a 10 to the, what did I say, 6? That's a 10 to the 24th. At 10 to the 24th, a million doesn't matter. A million is nothing. Make sense? Really important that we understand it. So we can't change this n to the fourth by adding, and it doesn't matter. I could put 10 to the 600. And there's an n to the fourth. No constant can compare. The important thing is we look through all this noise and find out what's really important. In this case, the 5/8 didn't even matter because it was 5,000 or 5 million over 80 million. Any questions? If we were really pressed, if they're like, oh, are you sure by comparison with the harmonic series? We're like, oh, fine, I'll do a limit comparison test. Always start there. Always just threaten to do the limit comparison test. Fine, we'll do the limit comparison test. At that point, the person pressing should just back off. Like, oh, this person does know what they're talking about. You know what I mean? The importance of the comparison test is not being able to write the comparison test. The important thing to note in the comparison test is that you already know if the series converges or diverges. So if we have, for example, if I gave you the series 5 over 3n plus 7. We look at what's important. Does this converge or diverge? You have 3 seconds. Diverges. Converges or diverges? N to the third over n to the fifth, that's a 1 over n squared. So converges. This is just a 1 over n, diverges. Converges or diverges? What's the power on the n? N to the 1/2, and 1/2 is less than 1, so diverges. Remember, we're thinking about large values of n. We're trying to understand large numbers. The reason I'm making such a big deal about understanding these large numbers is that for the most part, humans don't do well with large numbers. Especially when those numbers aren't actually comparable. The amount of money that you have compared to the amount of money Bill Gates have, I don't care how much it is. If you have money because your parents go to work and earn a living, the amount of money that you have is incomparable to the amount of money that Bill Gates has. It doesn't even make sense to compare those numbers. That's like comparing, well, how does it compare the distance between here and San Diego and from here to the moon? Those aren't even comparable numbers. It doesn't make sense to compare those distances. One is just ridiculously larger than the other one. My diverges was a little messy. I don't know why. The idea is that we make snap judgments about these things. We look at these and decide immediately. Not just decide immediately, but know immediately by looking at the important things. Even if those things are like ridiculous. What here is the obfuscation? What am I trying to, what's the smoke screen? Cosine. What's the biggest value you can throw onto a cosine? What's the smallest value? -1, right? So the numerator is going to be between 0 and 2. Oh, that doesn't matter because the denominator is fucking n squared. Does converge or diverge? 1 over n squared converges. If you're not picking them immediately, that's fine. It's your first day. If you expect to be an expert on the first day, then man, that's just not how stuff works. It's like, I'm going to go try out for the Giants. Show up. It's like, oh, what baseball experience you have? Well, I've seen some baseball on television. That's not how this works. This guy that's not going to get hired has been playing baseball since he was 4. All right. That's going to do it for today. We got to do more than just these comparisons because these comparison tests, we need to know what's going on. But we need, more importantly, It's not that the terms go to zero, it's how they're going to zero. So we have to find the other ways that we can make things go to zero fast enough to get a finite sum. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.